Hello everyone. Welcome to our this week Robotics in Teaching seminar. And today we are very glad to have the Professor Chen Feng from the NYU to give this talk on the robotics. Professor Feng is currently an assistant professor at NYU, appointed cross department, including the civil and mechanical engineering and computer science. His lab AI Force aimed to advance robot vision and machine learning through multidisciplinary use-inspired research that originates from conventional engineering domains. Before joining NYU, Professor Feng was a research scientist in the computer vision group at Mitsubishi Electrical Research Labs in Cambridge, Massachusetts, focusing on the localization, mapping, and the deep learning for self-driving cars and robotics. Professor Feng holds a bachelor's degree in the geospatial engineering from the Wuhan University in China and a master's degree in electrical engineering and a PhD in civil engineering, both from the University of Michigan. And now let's welcome Professor Feng to give us this talk.
Thank you very much. Thanks, Paul, for the nice introduction. I'm really glad to share some of our recent works at this seminar at Rutgers. As you can see today, I will share a story of two popular cartoon characters, Baymax and Wally. They are my mascots to vividly explain my research in robotics and how self-supervised learning and weakly supervised learning is the key theoretical ingredient in my recipe towards creating those robots in real world. Okay, so yeah, my name is Feng Chen and I go by Chen. I'm an assistant professor in multiple departments. And before that, I was a researcher at Merle in Boston. And my research appointments are multidisciplinary because of my educational background. I started from photogrammetry, which belongs to geospatial engineering, and it overlaps significantly with computer vision in computer science. And this leads to my sort of unique graduate school research at Michigan on construction robotics, and also leads to my non-traditional publication records. In addition to the journal articles in civil and robotics, I also publish regularly in those top-tier AI conferences like CVPR. And this allows me to effectively generate and bridge new ideas between robotics and engineering. So currently I lead this AI Force lab aiming to apply robotics in civil and advance them for civil. This requires me to address the grand challenge of developing novel sensing, planning, and control algorithms for construction robots so they can interact with materials and humans in dynamic and unstructured environments. And my research methodology overall, from a high level, is multidisciplinary use-inspired research that not only provides fresh perspectives in robotics, but also could solve engineering problems. So in fact, my research on construction robotics is strongly motivated by some pressing societal problems. As shown here, safety and productivity are real problems in the society, especially in construction industry. And situations are getting worse because the new generations don't look at this industry as a rewarding field. So we have strong needs to develop and adopt more robotics and AI technologies. One may want to learn from the manufacturing and transportation that significantly benefit from robotics. Companies like Tesla and Google have attracted lots of new talents by their robotics factories and self-driving cars. But I want to point out here that several unique challenges are for construction robotics. Unlike manufacturing, construction environments are usually unstructured and dynamic. And unlike self-driving cars, construction robots need more material manipulation and human collaboration. Therefore, fundamental research are required to create better eyes and brains for those robots. To create better eyes and brains, we supervised learning with deep neural networks has achieved great success on images and videos. However, it heavily depends on large amount of human annotations in training. But human annotation is often tedious, costly, or not even available at a large scale in engineering due to the need of expert knowledge. So to avoid getting addicted to the supervised learning paradigm, which is believed to be the opium of AI researchers, the theoretical foundation of my work is self-supervised learning, which is the real cake in AI. It means to train the AI using raw data at supervision. And here is an example I assume most of the audience here are familiar with, an autoencoder that compresses an input image into a low dimension code word, and then try to reconstruct the input signal from that code word. And here, the self-supervision of the encoder and decoder functions is to reduce the reconstruction error between the x and x prime. And after training, what we get are all the latent codes will uniformly, will form semantically meaningful clusters that helps robots recognize different data patterns. To better explain how self-supervised learning are used in robotics, my story will contain two cartoon characters. The first one is Baymax from the movie Big Hero 6. It is a balloon-like robot, which represents soft robotics. And the second one is Wally, which represents mobile robots, or more specifically, mobile manipulators. Both the soft robotics and the mobile manipulators are emerging in robotics, and their applications in engineering have just begun. So next, I will explain how we use the self-supervised learning to create a smart Baymax. So as you already saw through Baymax, robots are not always rigid like transformers. Robots can be made from soft or compliant materials. For example, balloons, silicon rubbers, or through origami or paper folding. Because soft robots have high flexibility and adaptability to complex environments, they are intrinsically safer to work with humans more closely together. So therefore, they can have huge impacts on our society. In construction, wearable soft exoskeleton have the potential to collaborate with human workers through physical augmentation. In material handling, they could help workers to better manipulate objects. In healthcare, they could be used for surgeries or rehabilitation. However, even with all these advantages, soft robots have not yet been widely adopted in the industry. And one of the reasons, from my perspective, is due to a long-standing hard problem for soft robotics. It is rooted in the almost infinite degrees of freedom of soft robots. This makes it difficult to model, estimate the state, and closed-loop control them. One example is to illustrate such a challenge is the proprioception problem. It means the ability to sense your body's pose and motion without external inputs. And now if you close your eyes and try to touch your nose, and try to see if you can do it. If you cannot do it, I would recommend a doctor's appointment. For rigid robot arms, this is classic, right? You can model them with the so-called DH convention, and then you can sense the parameters in those representations through angular or linear sensors. But for a soft body like Baymax, it could be bent and twisted at anywhere. So what can we do? Well, existing methods are either physics-based or data-driven. The physics-based models, such as the finite element model methods, FEM, have been used to model certain types of rod-shaped soft robots, but many of them cannot directly solve the proprioception. And even if they can, their computation are usually too slow for robotics applications, and not to mention how tedious it is to calibrate those models. And the data-driven ones use deep learning, such as a convolutional neural network or simply a multi-layer perceptron. For example, Cornell adopted the CNN to estimate the bend and twist angle of the soft body, and Georgia Tech adopted MLP, the multi-layer perceptron, to predict a soft finger's 3D tip position. But these angles or tip positions are oversimplified and cannot reflect changes caused by the environment and miss the soft robot's real advantage. Instead, we believe soft robotics needs a learnable full body representation. To represent the full body surface, instead of just a few angles or key points of a soft robot, 3D point cloud is a natural option. A 3D point cloud is just a list of 3D points recorded as a n×3 matrix, where each row corresponds to a 3D point. And this is an important data modality that has lots of applications in different engineering domains. For example, the LiDAR in self-driving cars, 3D scans in reverse engineering, CAD mesh models in manufacturing, building information models, and terrestrial laser scans in civil engineering, and the digital surface or elevation models in GIS. But point clouds are intrinsically different than images, where CNN succeeded. We say a point cloud is an unorganized or unordered representation because if you simply swap the rows of a point cloud matrix, that n×3 matrix, it doesn't change the corresponding geometric shape, right? You're just changing the order you record those point clouds, those points. Can deep neural network really process 3D point clouds? The answer is yes, and thanks to the recent advancements in 3D deep learning, such as PointNet. And PointNet basically uses a pointwise MLP and channel-wise aggregation to achieve point order invariance and enables end-to-end deep learning on point clouds. And this backbone network allows people to generalize image autoencoder we discussed before to point clouds. And the encoder will map a input point cloud to a low-dimensional code word, and then the decoder will try to reconstruct it using a chamfer distance to measure the similarity between the input and output point clouds. The question is how to reconstruct an unordered list of point coordinates from a compact vector. Well, the naive way is to simply use a large MLP. Like here, you use a large MLP that will map this k-dimensional code word back to a 3n dimension vector, and then you reshape it to a n×3 matrix and call this as the reconstruction result. But this approach has some significant drawbacks. The decoder contains too many parameters to be optimized efficiently because n is typically huge. And moreover, once you train this MLP, after it is trained, the decoder will always reconstruct the same number of points, regardless of the input complexity. Is there any way that we can do better? And of course, and our key inspiration comes from origami or paper folding, which can be viewed as a 2D to 3D mapping. And this inspiration is based on our observation that a 3D point cloud are often obtained from object surfaces. For example, they can be sampled from CAD mesh models or scanned from line-of-sight sensors such as LiDAR. And because 3D object surfaces are intrinsically, at least locally, 2D manifolds, they can be transformed from a 2D plane through the paper folding operation. And to cope with complex surfaces, we will need non-standard paper folding operations like tearing, stretching, and gluing, in addition to folding. And with this insight, we just need to design the decoder network to mimic, from a high level point of view, to mimic this highly nonlinear paper folding process as a more efficient and flexible way to reconstruct 3D object surfaces in a point cloud autoencoder. So this leads to our novel point cloud autoencoder named FODINET, published in 2018, and it has been cited for more than 600 times already. And its network architecture is shown in this figure. And essentially, a FODINET decoder is a parametric surface that is deeply learnable. And here I want to make an analogy between FODINET and the NURBS surface, or basically, if you're not familiar with NURBS, you might have heard of a B-spline surface, which is basically the same. And they're often used in engineering, like finite element methods and isogeometric analysis, those type of methods, as a way to model and represent 3D shapes. The code word C here is like the control points in those B-spline or NURB surfaces, controlling the shape of the object. And the decoder network parameter theta are like the knot vectors or weight vectors controlling the basis functions. And both FODINET and NURBS or B-spline surfaces are mapping 2D parameters t to a 3D point x. Okay, and the only difference is that FODINET is fully differentiable with respect to any of its of those involved variables. While the NURBS knot vector, the knot vector in NURBS are not differentiable at all. And the NURBS basis functions are much simpler than the f theta, which is implemented as a pointwise MLP here that will map a k plus 2-dimensional vector down to 3D. And here, this origami-inspired decoder fully addresses the previously mentioned issues because the MLP is not depending on the number n anymore. Therefore, it is much lighter weight and more flexible for different surface complexities. And what's interesting about FODINET is that this self-supervised process automatically discovers different folding plans for each 3D objects in the dataset. Because FODINET discovers this 2D to 3D mapping, we can then calculate the curvature fields here, as shown here, and 3D neighborhood distance field on the parametric surface. And then we can visualize this field on the original 2D domain, which is the paper. And this curvature field corresponds to the folding creases, and the distance field means the tears and the stretches. This allows us to visualize the automatically learned folding process, as shown in this animation. Paper plane is gradually folded to deform and folded to the 3D shape of a sofa. If I print these on a piece of elastic paper, I can literally recreate any complex 3D objects. And in some sense, we build an AI that taught itself to become a paper folding master through self-supervised learning. And how cool is that? And by the way, if you have any questions, feel free to interrupt me. So now we're finally ready to address the hard problem for soft robotics. We could use the FODINET as the learnable representation of the full body of a soft robot. And of course, we cannot directly use it as is, because FODINET is an autoencoder whose input must be a point cloud already. But that input is exactly what we need to estimate in the soft robot proprioception that we just discussed. So we have to change the FODINET encoder from a point net to a convolutional neural network that can produce a latent code word from images. And this images should be captured by self-observing cameras that are embedded inside the soft body. And we could use other self-observing signals than images, such as strain sensors, but cameras turns out to be the most suitable ones due to its high dimensional output with a relatively low cost. And after that, you just need to collect a large set of images and corresponding 3D point clouds of the soft body, which can be easily captured offline using external 3D cameras like Kinect. And then you can use this data set to train the network to fold the full body shape based on the observed images. And after training, the system is ready to estimate 3D shape of soft robot from only internal cameras without the external 3D cameras anymore. And we call this method Deep Sorrel. It is the first method in the world that can provide full body shape estimation for soft robotics in a proprioceptive manner. And you can see our data collection setup on here. We put 5 low-cost USB cameras inside the soft Baymax toy filled with balloons that has random color patterns to provide a rich visual features in the camera views. And the Kinect camera and the green screen is used to easily capture the ground truth 3D point cloud of the full body surface for training. And the video shows our shape estimation result in real time. The color here means the depth value, which is the 3rd dimension. And the 5 images are taken from those 5 cameras, and we're using them together to estimate the shape like this. And if you compare this versus the ground truth, you see they're very similar to each other with high resolution. And here we're showing a video, but our method does not rely on the video, on a sequential input. Our method just takes this 5 images at any time to estimate the shape. And because of the folding net decoder, this low-cost system is very lightweight, so it can run at more than 400 frames per second, achieving high shape estimation accuracy with less than 1% relative error, corresponding to a couple millimeter in this case. And the Deep Sorrel has been published in IEEE Robotics and Automation Letters, and also presented in its flagship conference, ICRA, in 2 years ago. So here we show more results and analysis. The top figure shows the qualitative accuracy of Deep Sorrel. We align the estimated 3D shape onto the captured RGB images and color code the discrepancies. Blue means error is below 5 millimeter, and light green means 10 millimeter error. And the results on both the Baymax and the Blue demonstrate the high accuracy, estimation accuracy, considering how large and complex those soft bodies are. We also study the influence of different image resolution from 16 by 16 pixels all the way to about 200 by 200 pixels. And from the this table, you can see that Deep Sorrel is not very sensitive to image resolution, which means that the system can be made even more compact in the future. And our speed analysis on this table shows that if running on desktop with GPU, the speed is over 400 frames per second. And even if we're running this on a resource-constrained system like wearable robots, we can still achieve interactive frame rate, which is important for robot control. So to recap this part, I showed that soft robotics can have huge impact in the future of construction because of its great potential in human-robot collaboration. However, its almost infinite degrees of freedom has a significant is a significant roadblock. And I hope I have excited some of you by the origami-inspired self-supervised 3D deep learning method, which provides a learnable full body representation for soft robots and enabled the very first full body shape proprioception for the soft robot, for soft bodies. If there is any question about this part, feel free to ask, because next I'm going to move on to WALL-E. Okay, I assume you are saving your questions to the end. I guess I can move on to the next part. Now let's talk about WALL-E. Different from Baymax, which has a strong focus on collaboration, WALL-E represents the fully autonomous mobile robots or mobile manipulators. As shown in this movie, the little robot needs to find materials, pack them, into cube-shaped building blocks and then properly assemble those blocks accurately and layer by layer into high-rise structures. In robotics terms, WALL-E needs to simultaneously navigate itself in complex environments and modify those environments. Believe it or not, this is not a simple task as it appears in the movie. There are two fundamental challenges in robotics theories for WALL-E. I will talk about each of them separately. The first one is localization. Due to the urban canyon effect, GPS won't be accurate or robust enough to provide centimeter or millimeter level global positioning, not to mention GPS does not estimate orientation. So WALL-E must rely on local sensing for robust localization. And visual localization is a very appealing direction in the last 2 decades, because it does not require any physical sensing infrastructure, unlike GPS or those RF-based, like a beacon-based positioning techniques. All you need is some kind of local sensors that you can put on a mobile agent that can observe its local environment. And then visual localization will utilize these local sensors to estimate its position. So existing visual localization methods can be organized into 2 groups. One group, which is a more classical one, are sort of like SLAM-based or simultaneously localization and mapping-based. They require the correspondence between the local measurement and landmarks of those measurements in a global map. And also they require to know the landmark positions. This typically means you have to go through a complex mapping process, which is sometimes not robust, and often requires expert knowledge to tune hyperparameters in different new environments. Another group tries to implicitly address the correspondence and landmark requirements using the recent deep neural networks, which is quite appealing because once it is trained, the system just needs to use the network to localize itself. But there is a difficult assumption in this learning-based approach because it needs ground truth poses for training. However, the ground truth poses are not necessarily easy to obtain. We'll explain more about this in this slides. Actually, PoseNet is the seminal work in this direction. It is basically an absolute pose regressor that uses a learnable function to map any kind of local observation to the position or pose where that observation is taken. So, and then you can simply use supervised learning like this to minimize the loss function, and then you can train the system like that. Is there any question? I hear. Okay. Our key idea in this work, which we call it as deep GPS, is to not train PoseNet with ground truth positions because we typically don't have those. But we're going to design this weakly supervised learning through pose constraints. So you can consider the training data set as a graph where the nodes are local observations and edges are pose constraints. For example, it could be distances between any 2 poses or relative angles. And they're relatively trivial to obtain in robotics. For example, distance can be obtained from wheel encoders or the inertial measurement units, IMUs. The loss that we will use will minimize the constraint violations. In this case, this is a constraint function that says for any edge in this graph basically requires a constraint, and you say, I will use this PoseNet and compute the constraints and compare this constraint with the ground truth constraint that can be easily collected. And then we can solve the whole, we show in this work that the PoseNet can be trained in this way, in a more indirect, weakly supervised way compared to the full supervision in the original PoseNet. And the reason why this system, by training this loss function, is you are still able to optimize and find a desirable pose net like this f theta is that it has an interesting, nice connection with the old technique called multi-dimensional scaling. Basically, what we're doing is we're supervising such a pairwise function that estimates a Euclidean distance matrix, if you consider the constraints as distances for simplicity. In the interest of time, I'll directly jump into the experiment of this part, because in the third part of my talk, I want to show something even more exciting. But here are some experiments that we did for this very simple idea, simple yet effective idea. We first tried it in the toy example, which is numerically simulated environment that have all these 2D landmarks. And the sensor, the robot, a virtual robot can obtain distances to those landmarks. And we showed that, hey, we achieve comparable result versus PoseNet, but we don't require the ground truth position. All we need to do is to drive this robot running through different straight line segments and then record the distance you traveled along those line segments, and use those as the constraints to supervise the system. And we show that, well, this can be done. But next, more interestingly, we're testing this in a virtualized photorealistic environments in Habitat Sim. That was developed by Facebook. So in this case, we're switching our observation signal to an omnidirectional image that's looking above at the ceiling. And obviously, you need to change your PoseNet function to a convolutional neural network. And again, we're showing that we achieve comparable or even more robust localization compared to PoseNet, when especially if the poses have noise, because we're using weakly supervised learning, we're more robust to those noises. We also did this in real world environments. We put visual landmarks, like those visual patterns on the wall. And then we again use this, those are used to provide ground truth. Our setup is the same as the previous experiment, where we have a real camera observing the ceiling upward. And the image, the observation is still an image, and the network is still a convolutional neural network. And you see, in this case, in real world, we actually performs better, not just comparable, we're actually performing better and more robust than PoseNet. And the reason is, in real world, your ground truth is often obtained with noise, but because we're using weakly supervised technique in deep GPS, the network is not confused by those noisy ground truth positions. So deep GPS actually achieves better performance, as shown in this figure, both if you look at the RMS or even the max error. So to quickly recap this part, we show that WALL-E, or a mobile robot, needs a simple and robust localization method. And we can use constraint-based weakly supervised positioning that benefits from both the simplicity of learning-based positioning and also avoids the challenging ground truth collection process, which is typically required by the previous PoseNet example. Okay. So WALL-E's challenge, in the previous part, I quickly skimmed through the first challenge in localization. However, WALL-E's challenge is more than just localization. Not only does WALL-E needs to plan for its traveling trajectory, but also it needs to plan for construction during its manipulation process. In fact, the WALL-E's challenge lies in the interdependency between localization and planning. And to illustrate this challenge, let's look at two different WALL-Es trying to build the same square-shaped structure. Because there is no GPS, they need to maintain a map of the environment and themselves to track their locations and remember where blocks were built. And this little blue, I hope you can see, the little blue and orange dots shown on the top left of the map here are their belief about the block positions and their own trajectories. And when the gray Wall-E made a bad planning and built two similar structures in figure C here, this creates something called perceptual aliasing in robot perception, which confuses the robot localization because each robot can only observe a local region surrounding itself. And meanwhile, the red Wall-E, the construction plan for the red Wall-E is more strategic and better facilitates its localization. And now, because the gray Wall-E mistakenly think it was at the other side of the square, its next construction activities are completely wrong until it cannot build outside of this job site. And this construction error will further cause planning confusions that will bring the whole process into a negative feedback loop. Comparably, compared to this, the red Wall-E can accurately finish the construction because it better accounts for the interdependency between localization and planning. So looking at this mobile construction problem from a more abstract and theoretical perspective, it is actually a POMDP, or partially observable Markov decision process. A POMDP problem is defined by the following key variables: the state, action, observation, transition function, and reward function. And it's illustrated in this figure in the context of mobile construction. This grid-like environment in this figure and the term MDP might remind some of you the Go game, which is a classic MDP problem. And in fact, the main difference between the two problems is that in mobile construction, it is only partially observable. And this is the root cause of the localization planning interdependency challenge that we just discussed. And although AlphaGo significantly outperforms human, AI still cannot solve mobile construction yet, even in this highly simplified and theoretical setup. As shown in this plot from our recent paper under review, the x-axis contains different mobile construction problems from 1D to 2D to 3D, and the y-axis shows various AI's performance compared to with two human baselines, which are the brown and the black dashed lines. As you can see, no AI can surpass human performance yet, and they perform badly when it comes to 2D and 3D cases, while human can solve this problem very well. And I guess some of you might be wondering, how is this problem connected to real-world construction? And in fact, I actually abstracted this problem from the robotics bricklaying, like what I did before and what's shown here in ETH Zurich. Besides bricklaying, mobile manipulators has other underexplored areas, which is construction 3D printing. And current 3D printers are mostly following the same principle, where gantries or fixed robot arms are used to move the printhead accurately in a predefined limited space. And this includes desktop plastic printers, robotic arm-based printers, or large-scale gantry-based printers. And with all these great achievements, I want to point out some fundamental limitation for such 3D printers. And first is the scalability issue. If you want to print a house, your printer has to be bigger than that. And second is the collaboration difficulty, which brings slowness in this process, because gantry-based printers are not easy to work with each other to print the same structure together. So switching to a mobile manipulator naturally overcomes these issues. But mobile 3D printing is simply mobile construction on a continuous domain. When you remove the gantry, how do you actually localize the print head after the mobile base moves? And apparently this question has been asked before, although in my opinion, those existing answers are still not enough. And one type of methods rely on infrastructure-based mechanisms such as GPS or some specially designed printing plates to facilitate the global localization. But we already said that GPS are not accurate enough, and sometimes it's neither available nor scalable, such as in indoor or even in like extraterrestrial scenarios. Another type relies on SLAM. which is the technique for self-driving cars to localize them when GPS is not available. But this is fundamentally problematic because a basic assumption for SLAM must be violated in mobile construction. SLAM assumes a mostly static environment, but mobile printers needs to actively modify this environment. Therefore, as agreed by researchers in this emerging field, mobile construction still need a more flexible and accurate localization method. And as discussed before, this is a very hard problem in both theory and practice. So for a long time, I did not know what to do except for scratching my head until I saw this. And suddenly I realized that a cat is a mobile manipulator. And hey, if cats can be guided by a laser pointer to different locations, why can't I use optical signals to guide my mobile robot equipped with cameras? So in this way, I can bypass the interdependency challenge by decoupling the localization with planning, because localization will be optically guided without affecting the planning. So this leads to our design of the projector-guided mobile manipulator for desktop plastic 3D printing, for quickly testing the feasibility and performance of this idea before we move on to bigger platforms. So the system contains an overhead projector that can project dynamic point patterns received from the central control station. And this pattern is observed by the mobile printer as an image. And then the pattern information on the image is then extracted from the image and sent back to the central station, which calculates the desired velocity of the mobile base as well as the print head. And this control information can be used, is sent back to the mobile printer to guide it following a pre-calculated trajectory that can fulfill the 3D printing. And because this is desktop 3D printing, we need to achieve millimeter level precision on the print head positions. So the newly printed material layer will be accurately supported by the underlying layers. And therefore, our next question is, how do we compute the mobile base, the velocity of mobile base according to the observed point pattern, so that we can navigate and control the robot precisely. And controlling a robot to follow a visual pattern is termed as image-based visual servoing, which is typically studied for fixed robot arms in a robotics manufacturing factory. And the key of this IBVS is to find the interaction matrix LE, which is basically the Jacobian matrix of the image point dynamics with respect to the robot's motion. And this interaction matrix describes how would an image point U move according to a small motion in the robot speed, which contains the linear velocity and v and angular velocity omega. And after finding multiple interaction matrices at a different image pixel, we use the least square principle to estimate the optimal robot speed by multiplying the pixel displacement with the pseudo inverse of the interaction matrix and the control gain lambda. The computed optimal speed will then be applied to the mobile base to control the robot, and the control goal is to make the observed point patterns stay in the fixed pixel location in the middle of the camera view. And therefore, when the projector moves this printing pattern, this point pattern, the resulting pixel displacement will generate a non-zero robot speed that tries to reduce the displacement as fast as possible. And okay, this classic IBVS pipeline works well in robot arms because 3D cameras can be easily mounted on them, and the LE can be computed using pixel depth values from 3D cameras. But for our mobile printers, it is not easy to use 3D cameras due to factors like bulkiness or power consumption. When we are forced to use 2D cameras, can we still use this general pipeline? Well, here the self-supervised learning becomes essential again. Think about the meaning of this interaction matrix. It means how the image point moves corresponding to the robot movement. In a data-driven spirit, we can collect some data pairs between such correspondences, and then we can train an MLP as the function that maps from a pixel U to a 2x2 interaction matrix. And the training process minimizes this loss function here that tries to find the best MLP to explain the observed data pairs. What's cool and novel is that this whole process are fully self-supervised, and the data collection are done without human attendance. We simply make the robot move randomly with various robot speed, as shown in this video. And we record those speeds and the corresponding image points movement, the image points displacement on the image plane between the current and the previous frame. And this can be easily computed using the optical flow algorithms, which is mature in computer vision. And in this way, after the training, we obtain an image-based visual servoing system without the need of any 3D cameras, and we turn this as a learning-based visual servoing. Okay, let's see our Wall-E in action. So we first did a simple 2D trajectory painting experiment to test the trajectory accuracy. The top left shows the camera view. Here is the camera view, and the whole printing field is about 2 meters by 2 meters, which is much larger than most of the desktop 3D printers that you can buy. As you can see in the table, our painting trajectory, our painted trajectory has an average error of less than 2 millimeter, and the max error is less than 1 centimeter. And this means about a 0.1 to 1% relative error, which makes me really happy, because that means we can do 3D printing. And here our Wall-E performing a actual plastic 3D printing of a square-shaped structure. In this experiment, we choose to print a small-sized sample so that we can accurately measure the ground truth by a 3D scanner later. And here is the photo of the printed structure. It's about 11 by 11 by 3 centimeters. The design wall thickness is 2 millimeter, and we measure the wall thickness with an average of 3 millimeter and a max 4 millimeter. And you can see the 3D scan with color coding to show the printing error. As you can see, the printing quality is not as good as commercial 3D printers yet. And one of the reasons for this is because it is just a prototype system that we built in 6 months to validate our CAD versus laser idea. So there are lots of rooms for engineering improvements. And more importantly, we deliberately choose a very hard mode of mobile 3D printing, which is the continuous printing. Unlike other mobile 3D printers, our mobile base will be constantly moving while during the whole printing process, while the easier way is to move the base to a spot, stop it, and only move the robot arm to print some portion of the structure, and then move the base to another spot for the next portion's printing. And this reduces issues like vibration to improve the quality. And we choose this hard mode because we want to test our methods potential under the worst case scenarios. And it also offers new possibilities for mobile 3D printing that nobody was able to show before, because continuous printing of materials might be needed for certain structural integrity requirements. And to show something that no existing desktop 3D printers can do, we scale up the experiment and use 2 Wall-Es to simultaneously print a sword-shaped structure of 80 centimeters long, 30 centimeters wide, and 4 millimeter high. Again, the quality of the printing shown is worst-case scenario performance, just like the previous example. Something significant to note here is that to print something like this, traditionally, you will need an industrial-grade 3D printer that can easily cost you between $50K to $750K US dollars. While our prototype system costs no more than $1,000 per robot, and this cost will further reduce when we mass produce the system. To recap this part, I hope I had excited some of you that mobile manipulators could achieve larger scale and faster 3D printing with more flexibility, although the fundamental challenge is not just in engineering the system, but the lack of theories in joint localization and planning. I hope I had also convinced you that the innovation in our projector-based, projector-guided self-supervised visual servoing, which partly addressed the challenge and really enabled our Wally printers in real world. So in summary, I told you a story of Baymax and Wally in my research as two important types of construction robots. And I also showed that they can be designed more efficiently with self-supervised AI. And the key take-home message is that although raw data collections could be cheap, but human annotation is usually more expensive. So we really need self-supervised learning or weakly supervised learning. And moreover, self-supervised learning could enable easier incorporation of prior knowledge when we design such engineering systems. Last but not least, I would like to thank all my students, collaborators, and the funding agencies for making all this exciting and ambitious research possible. So with that, I will stop here, and I'm happy to take any questions.
Thank you, Chen. So very interesting talk. And any questions from the audience? Yeah. If you have any questions, you can unmute yourself and directly ask questions.
Yes, I have a question regarding the limitations of the guided Wally robot.
Mm-hmm.
So given that the robots of, a certain dimensions, wouldn't the limitations of how many you could have, let's say, within a given area limited by either the size of the robot or the, I guess, 2D area of the, what's it called? The thing it's following. Sorry, I forgot the name.
The trajectory?
Yes.
Oh, sure. Yeah. But I wouldn't consider that as a limitation, because if you consider the existing solution, it's just like if you want to build something, you need to have a gantry, a frame that is bigger than that thing, in order to print the structure. But when you use mobile robots, you can, of course, the robot will occupy some physical area, but it's still relatively small and compact. And more importantly, the key advantage here is you can use multiple. You can use multiple printhead working on the same structure simultaneously, compared to the previous 3D printers. So if you use a 3D printers, you might know that you need to wait, because it only have one printhead, and that printhead needs to do this layer by layer printing. And usually you need to wait for longer if you're printing larger structures. But when you have this mobile manipulators, they can collaborate with each other. They can work on different parts simultaneously. And in that way, you can sort of like, so I'm making an analogy between the single thread versus multi-thread in computer science. So this is in similar spirit.
So I guess another question I have is regarding how would you stabilize the robots, or is this currently only tested on flat, smooth surfaces?
Right now, we are only testing on a complete flat surface, because we don't need to make it arbitrarily difficult. In the future, we do have plan to test this in real-world non-flat terrains. And that requires us to use methods like model predictive control to adjust the plan in real time. But right now, we're in the first stage 1 of this project.
Okay. So how do you go about powering the robot?
Right.
Yeah.
Right. Right now, this robot is battery powered, but it's easy if you want to run it for a longer time. It's easy to use a tethered system to do power. Actually, you also need to think about the material. For the plastic printing, it's easy that we store the materials at the base. But if you want to do longer time printing, you obviously want to do a tethered system. That adds certain extra complexities when you plan the trajectories. You want to avoid the the multiple robots, their tethering system needs to avoid each other. But for now, just a battery. We're doing this on purposely using battery-powered systems. So you do not need, and our battery can easily last for several hours. So it's not a big issue at the moment.
Mm.
Cool. Thanks for the question. Any other questions?
Hi, Professor.
Mhm.
Can you hear me?
Yes.
Yeah, I think the last project, the project guided 3D printing is very impressive. But I have one question that I'm wondering how the machine learning method help in that project. I mean, I know this like printer is guided by a laser sent by the project, but what's the how the machine learning method get advantage compared to like we just use like a sensor to track the laser? Why we need to use a machine learning method?
Right, exactly. So thanks for the question. I think the self-supervised learning method is actually the key enabling factor. Without that, we cannot actually do this. First of all, when you say sensor-based method, I assume you're talking about some kind of like IMU or will encoder. So if you ever worked on mobile robots, you will know that we can never trust those kind of like a dead reckoning type of localization method, because you need to do integration of IMU, double integration of IMU, or if you're using will encoder, you need to go through similar process. And the issue about those integration is the error will accumulate, especially if the will have some slippage, and those are not captured by those sensors, and they will be propagating in this dead reckoning system, and very quickly, especially when you make some turns, very quickly the position becomes unreliable, and then the structure you print will never be able to be self-supporting, because when we do this layer by layer printing, you need to make sure you achieve millimeter level accuracy. When you talk about other type of sensors like 3D cameras, like what I mentioned in the slides, that's the traditional method. So traditionally, when people put this 3D camera on a robot arm, like big industry robot arm, and they can do this problem, that's already like a well-studied problem. However, the issue is when you're using a mobile robot, we just talked about the power issue and all those. We cannot put, we cannot just put a 3D camera in the system. So it consumes more power and also cause difficulty in terms of the design of the system. So we're forced to use 2D cameras. And when you're forced to use 2D cameras, the issue is this visual surveying method needs a key piece of information, which is the depth of each pixel in that image. And if you don't have that depth information, you won't be able to compute that interaction matrix, which is essential for computing the control of the robot movement. So we solved this using the self-supervised learning that actually removes the requirement of using a 3D camera, and more interestingly, even more appealing factor in here is this whole system doesn't require almost no human attendance. You just turn on the system, you bring this robot to any flat surface, you set up the projector, you turn on the system, and the robot will automatically, just like here, it just makes some random movement to collect data and then calibrate itself fully autonomously without human. Like compared to previous methods, you need to, more classic methods, you need to calibrate your camera. You need to, like if you ever took any computer vision course, you know John's method. You need to use John's method to calibrate the camera, and in addition, you need to do the hand-eye calibration, which finds the relative position between the camera and the mobile base, which is another tedious process. And you need to do this whenever you restart the system in a new environment. And here we can do this fully autonomously. That really reduces the requirement and make it really user friendly. And this is not possible without self-supervised learning. Yeah.
Okay, I got it. Thanks for your answer.
Yep. Thanks for the question.
Other questions from the audience? So Chen, actually, I have two questions about your learning part. And the first question is that, so here you, for the backbone model, you typically use those the CNN based or like the point cloud oriented models. So I was wondering, so things like in the computer vision right now, like the vision transformer has become the kind of very popular. Whether the kind of potential application or adoptions like for the transformer or vision based model be used in this type of application?
That's a good point. So first of all, regarding the backbone model, we do not have a specific preference. It really depends on our input modality. If our input is a point cloud, we use like a 3D deep learning backbone like PointNet, PointNet++, those things. If it's an image, obviously CNN, ResNet, or VGG. If it's a structured representation, we use MLP. We haven't tried transformer for the following reasons. Transformer is computationally heavy. The computation cost increases quadratically compared to a CNN. So we don't like we're a little bit skeptical about their use and advantage in robotics, especially if you consider all these mobile robot or soft robotics where we want our system to be able to be used in real world resource constrained platforms, and in those cases we haven't start trying transformers yet. Although recently we saw works that like SegFormer. I have my friend and my previous intern at Merle, Zhiding, they have done this really good work called SegFormer, using transformer to do semantic segmentation. And he told me that transformer is actually not so bad in terms of the speed and memory consumption. But I haven't seen any example of using that in, like, for example, Jetson type of computational platforms. They're all heavy computation, heavy GPUs that I cannot imagine putting them in my robots. Maybe in a self-driving case, a self-driving car like Tesla or Google, that is possible, but definitely not on my robots.
Okay, thank you. And you have another. I have another question that about your self-learning or the weekly supervised learning part. So, so here, so it looks like so you don't use like the because in the image in the image classifications for this when we talk about the self-supervised learning, like we typically adopt the strategy of the using the so-called contrastive learning. And so
that's right. Yeah.
Yeah. But here it looks like that actually you use kind of the very smart choice of the
that's right.
The penalties to connect the unlabeled data to your law. So
that's right.
I was wondering, so whether those type of the existing contrastive learning philosophy can be used here, or if not, why?
That's a very good question. Well, we actually have a new CVPR paper accepted this year using contrastive learning, a newly designed contrastive learning for visual spatial reasoning. So on our work that is more AI oriented in the design space, not robotics, we do use lots of contrastive learning and self-supervised learning for representation learning. For these three robotics applications I introduced today, it's more about we have prior knowledge as engineers about these engineering problem, and we're trying to incorporate those into our learning process. And we find either self-supervised learning or weekly supervised learning is a good way to incorporate those prior knowledge. So in that sense, my definition of self-supervised learning is broader than the self-supervised learning that is commonly referred to in the literature, which is constrained to those, for example, like autoencoder or contrastive learning or this kind of like a jigsaw puzzle, those type of like colorization, those type of things. They're really solving more classic, more, I would say, more system one type of problems, like for a task agnostic process, where in almost all my talks, all the work that I explained today, they are task dependent. They're related to certain tasks, downstream tasks. So that's a difference. But it's a good question to ask whether those task agnostic self-supervised learning could be a good pre-training step before these works to learn for example, we can warm up this postnet function using self-supervised like contrastive learning, and then we see if we can benefit from that process. This is an unanswered question that may be worth investigating in the future.
Thank you very much.
Yeah.
So any other questions from the audience?
Actually, I also have a question.
Mm-hmm.
So, hi, Professor Feng. May I ask how do you find a balance between the trade-off between the network performance and the speed? Because we all know that deeper neural network also usually brings a better prediction performance, while it also causes heavier computational cost. How do you find a balance between this?
That's a very good question. My short answer might disappoint you. We don't, because right now we're focusing on making something like work first before optimizing their performance like speed. So in all these works, even though you see some of the work like the Baymax one, I talk about those speed, but it comes as a byproduct. We never on purposely optimize the system in terms of speed. It's just like we found that it works well in different kind of computational systems, because our focus right now is focusing on enabling those cool engineering, addressing those engineering needs. We're not yet optimizing this computational system. I think there are much work to be done. For example, in some of like the Baymax example, we show that we can here we show that you can optimize the image resolution. You can optimize. You can even optimize the network architecture, how many number of layers you really need, or you can use the distillation after training the network. All those things are good directions that's worth to be investigated. It's just like from the robotics and vision perspective, we're right now focusing on creating new abilities than optimizing the efficiency of those abilities. But there are many other groups in the community that does this, right? People using like several years ago, NAS was quite popular. Right now, sort of cools down a little bit. But I think network distillation would be something very interesting. That could be a potential direction. But I really, unfortunately, we haven't explored into that direction yet.
Thank you.
Mm-hmm.
I also have another question. So have you tried using attention mechanism in your method? So what do you think that the attention has the potential of improving the performance a lot?
That is a very good question. In the work that I discussed today, we do not specifically use any attention mechanism. No, not in the work that I discussed today. But in other works in my group, we do use to a certain extent attention mechanism. For example, the self-supervised spatial reasoning work that I mentioned, which is accepted to CVPR 2022. In that case, where the problem was given some 2D line drawings, how can we perform reasoning about its 3D shape and its orientation? We published two years ago in CVPR the data set called SPARE 3D, SPARE 3D, spatial reasoning for line drawing, multi-view line drawings. And we solved that problem using self-supervised learning. And in that case, we designed this contrastive learning architecture, which to a certain extent, you can think about it as having some connection with attention. But we in my group, we don't do that much about backbone network research. Maybe the only one was this FODINet that we did for 3D deep learning, which proposed a new backbone architecture for the 3D shape decoder. But after that, we didn't spend too much time in that direction. I just felt like that direction is there are too many competition in that direction, and it's not efficient for me as a junior faculty to spend effort on that. So we didn't continue in that direction. But I think attention. The transformer is definitely one of the big success, right, in using attention mechanism, and in vision specifically, it's becoming very successful. But again, I think I always need to consider like the connection to real world systems. That's the feature in my lab. All of our works, we want to apply it in real world engineering systems. So the low power consumption, speed, and all those, and memory requirement, and all those things are very, very important. With a small research group in academia like us, we are not as rich as Google or NVIDIA. We don't have that many GPU cards. So that's another limiting factor about the choices of our research.
Thank you for the explanation. I still have the last
No problem.
question. Yeah. May I ask, how do you control your robot? Do you use some algorithm like MPC, or just update the derivatives based on the dynamic system?
Right. Thanks for that question. So in the first two work, we don't do any control, right? The first two work are all like state estimation. We estimate the shape of the robot and the position of the robot. Although in the soft robotics direction, we're right now doing control. We have students working on that direction. In the third direction is the only one in today's talk that involves control, which is this visual servoing. Here we're not using MPC. We're just really this is really an image-based visual servoing process that is the control. And in this control, the key problem is to figure out that Jacobian matrix, and how can you automatically, without using 3D information, how can you learn to generate that Jacobian matrix? So this is our control method. When you need to, with more sophisticated scenarios, like when you're dealing with real-time perturbation, like for example, I think Stephen was asking that if my terrain is not completely flat, that increases vibration in the system, then we do need to use MPC to in real time adjust the pre-planned trajectory. But again, that is not our current focus. We actually, my colleague, Professor Ludovic Rigetti, he's more an MPC guy. I'm a more robot perception and computer vision person. So this is the level of control that we're doing in our group.
Thank you. I really learned a lot.
Thanks a lot. Yeah. Cool.
Okay, any other question from audience? If no more questions, so let's thank our speaker again. And thank you, Chen, very informative talk. And also thank everyone to attend our this week's seminar talk. So see you next week.
Thank you very much. Thank you for having me here. Bye-bye.
Thank you. Have a wonderful day. Bye.